Hi, good afternoon. My name is Daniel David,
And I'm Elizabeth Glick.
and our CM project is the piano key action. Now, on this slide, you can see an image of an upright piano action. And the way it works is that once a user presses down on the white area of the key, the hammer then hits the string and the damper backs off, creating a sound. However, once a user lifts their finger off of the key, the hammer then goes back to rest and the damper then makes contact with the string again, causing the sound of the piano to stop. And on a typical full upright piano, there are 88 keys and 11 octaves for 8 keys.
So we had to do reverse engineering for this project. The picture on the left is the picture from the eBay listing. So this is the part that we ordered without anything done to it. We ordered 2 of these, one to disassemble and the other one to actually experiment on, and that one's here. The picture in the middle is the model once we numbered all of the parts. So we took a Sharpie and we gave each part its own number. There ended up being 89 parts total. Once we numbered them all, we disassembled the entire model using a box cutter, needle nose pliers, a wrench, and screwdrivers. And along the way, we took pictures of the full assembly, sub-assemblies, individual parts, and exploded views. And an example of a sub-assembly is on the right there. That happens to be the damper that Daniel was talking about that moves on and away from the string. And as we did this, we measured each of the parts, and we also made observations of what parts either didn't need to be manufactured or could more easily be manufactured.
Now here, this is an image of a fully assembled upright piano action mechanism that we made in SolidWorks. We took all the measurements from during our reverse engineering portion of our CM project. And what this represents is a static model where it's not in motion. However, we were originally supposed to make a dynamic model where the key would actually move during SolidWorks. However, due to the only having access to the student version of SolidWorks, we did not have all the necessary capabilities and functions and features that we needed. This is a simple example of a single part that we took from the actual upright piano mechanism and accurately as possible dimensioned every single section needed. And these are piezoelectric sensors. They're usually found in guitars and they amplify the sound and pick up the vibrations. What they usually range from 15 millimeters to 100 millimeters in terms of diameter, and they give a voltage output.
So we wanted to mount 2 of these sensors, one to the key and then one where the hammer hits the string. The problem that we found is where the hammer hits the string is too narrow and we couldn't mount a sensor flat to it. So we ended up removing the string from the model, and we used part number 15 from the disassembled model and made sure that the front of that part was going to be right in line with where the front of the string would have been. So we marked that off with Sharpie. Then we drilled 2 pilot holes through the back here and through the block, and then put 2 screws through it to mount the block there. Then we took double-sided sticky tape and put it on the back of the sensor, and we made sure that it didn't overlap the 2 pieces of tape so that the sensor could be mounted as flat as possible. Then we cut the tape out into the shape of the sensor and stuck the sensor right on the block. But we had to make sure that the hammer was going to hit the center of the sensor and that it wouldn't hit where the wires were soldered on. Then we also mounted a sensor down here at the key. The key ended up being wide enough where we could just mount the sensor, just put double-sided sticky tape on it and just stuck it on there, and no modifications were required. So we made a LabVIEW program so that we could read the output from these 2 sensors. So this is the wiring diagram for that LabVIEW program, and this is the front panel for the program. So the 2 graphs on the left here represent the real-time waveform graphs. So these ones will always be showing something. The top one here is for the key, and the bottom one here is for the string where the hammer hits it. And when you press the Boolean button, if you press that at the same exact time that you hit the sensor on the key, it'll record 1 second of data, and that'll be enough to show the spike in change in voltage. So those are going to be displayed over here on these two graphs. Again, the top one is the key and the bottom one is the hammer. This front panel will also show you the min and max values. That's on the y-axis, the amplitude, and that is the voltage on these graphs. So it'll show you the min and max voltage, and we'll also show you the DC value and the RMS value, which is the AC value. We also wrote another LabVIEW program. This one is for tuning a piano. So basically what you do is over here you choose what key you want to be tuning. So in this case it's middle C. And LabVIEW was programmed to have the frequency that that middle C should be at. And if it'll show you whether it's flat, in tune, or sharp. So in tune is within 1% of that frequency that's programmed in LabVIEW. If it was below that, it would show that it was flat, and if it was above that, it would show that it was sharp. We also made a third LabVIEW program, and this one converts voltage to force. So this is the wiring diagram over here, and this is the front panel. It would show the waveform graph. It also has a dial for force, and it would show the numerical value for the force. These two, this one converting voltage to force, and the previous one of tuning a piano, because of how the project evolved, we ended up going in a different direction than these two, but we still programmed LabVIEW. So we wanted to make sure that these sensors would work as we hoped them to work. So we did a set of trials to make sure that they worked as they should. So we used a weight set ranging from 10 grams to 1,000 grams. And what we did, we hooked up a voltmeter directly to the sensor. And in this case, our sensor wasn't laying flat on the table, and that deviation as the weight was placed on it would throw off our results. So we ended up taping the sensor to the table to ensure that it was flat. Then we took the weight set and we did 6 trials for each one. And we used a random number generator to ensure that we were randomly placing the weights on here. So this example here, we placed the 10 grams on the sensor there, and we made sure that every time we placed a weight onto the sensor, it was from the same distance away from the sensor in terms of height. And then we would read the maximum voltage that was displayed here, record it, and we did this in Excel. And we had Excel tell us what the average was for each weight, so what the average voltage that weight was displaying. And that's over here. We made a graph of it. On the y-axis is the voltage, and on the x-axis is the weight. And you can see that for the first few weights, as the weight got larger, the voltage increased, and it's relatively linear as we expected. But then the last two, we found that it wasn't linear anymore, and we found that the problem with those two is that as the weight increased, the size of the weight also increased, so the whole entire weight was not being placed onto the sensor. So that was the problem. So in terms of our data, we excluded these last two, the 500 and 1,000 grams, we excluded because they were not consistent with our data.
Now on the left is a visual representation of when a weight is placed onto the sensor and is just left there.
So you can see the spike when the weight was placed on the sensor right there, and then you can see it slowly coming back down to 0. And the reason why it's slowly coming back down is because the sensor actually stores energy. And this also proves that it's the sensors are for dynamic use, not static, because the weight was left on the sensor, and yet it didn't stay up at 10 volts. It started coming back down, which proves that it's really only for dynamic use.
And on the right shows is a still image of when a weight is placed onto the sensor and the voltage just spikes up. So this is a very quick, momentarily thing that happens.
So as I said, when we were doing the reverse engineering, we made observations of modifications that could be made to this model. So the first one that we noticed is this strap here and this rod weren't actually being used in the model. There was no point for them being there. And so we removed them, and this would save the manufacturer money on the parts and also time, because they had to drill a hole where the rod went into this wooden piece. Another modification that we noticed was this threaded rod here. Now this pushed the felt out, but there was no reason why the felt needed to be pushed out. So we removed that piece, which again would save the manufacturer money on the part, as well as time to thread and tap, drill and tap that hole. And the last modification that we made is this piece here. They drilled 2 holes in it, one from front to back and one from left to right. And there was no reason for this hole, and it takes time for the machine to actually drill these holes, so we went ahead and filled it in. So we took voltage readings from both sensors before the modifications, and we did it again after we made the modifications. And we found that there was no varying difference between before and after, which means that the manufacturer could make these changes, could manufacture this model for cheaper, and they don't have to compromise the force that the hammer hits the string with. And this is the LabVIEW front panel. This shows an example of a weight being placed on the key. So again, this one's the real-time data. This one was 1 second of data. So basically what we did, we placed a weight on this key here at the same time that we pushed that Boolean button. So it recorded 1 second of data as shown here. This one on the top is the sensor on the key, and the one on the bottom is the sensor on the hammer. And as you can see, the hammer had a lot higher voltage that was produced. And the sensor on the key had about 1.16 volts, and the one on the string had about 10.43. So this means that the voltage for the hammer was almost 9 times that of the key.
And now one of the major aspects of the senior project was making a bill of materials. For the bill of materials, we labeled every single one of the 89 parts with their own item number. We specified the quantity of how many parts were replicated. We also labeled a description of what each part looked like and the type of material it's made out of. And in terms of measurements, we took our measurements from the SolidWorks drafting pages, and for the weights, we used a scale located in the Physical Health Science building, and which accurately gave us all the grams of for each part. And that concludes our senior project presentation. And thank you for watching.
Thank you.